HNSW spends memory on graph links. IVF-PQ spends recall to compress a million vector index. You'll select HNSW or IVF-PQ using an index selector that honors add-only updates and returns the choice, recall at 10 and bytes per vector. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Imagine a RAG assistant searching a million embedded document chunks. A brute force search can find the best matches, but comparing every query with every stored vector soon becomes expensive. Vector indexes make that search practical by accepting a small trade-off in speed, memory, or accuracy. HNSW and IVF-PQ solve the same search problem in very different ways. HNSW builds shortcuts between nearby vectors, like paths through a city. IVF-PQ groups vectors, then stores compact approximations instead of the original full values. We will build a fair comparison around the same vectors and queries. The goal is not to crown one winner. It is to make an index choice that matches recall, memory, and update needs. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need a trusted answer set before judging any approximate search. This snippet builds the exact Faiss baseline and stores top 10 neighbors for later recall checks. Approximate indexes only make sense if there is a trusted reference. So IndexFlat L2 holds the same 1 million vectors without compression or graph pruning. Exact add XB loads the database, and exact search XQK captures truth. The top 10 neighbor IDs each candidate index will be judged against. These random vectors stand in for embedded chunks in a RAG corpus, where missing a neighbor can mean missing useful evidence. The output confirms the corpus size and that every query has 10 exact neighbors. With the reference neighbors saved, we can test the graph approach that keeps full vector detail. This example builds the Faiss HNSW graph and runs the first approximate search. HNSW can be attractive when recall matters, but the graph adds RAM beyond the raw vector payload. IndexHNSWFlat dgraph_m stores full vectors, while HNSW.addXB constructs links between vectors that are likely to lead toward close matches. ParameterSpace set index parameter sets efSearch before search. Increasing efSearch usually explores more graph candidates and can improve recall, while decreasing it can reduce query work. The output shows the measured build time and confirms the search still returns 10 candidates per query. The graph is now working, but a memory-constrained deployment needs a different kind of compromise. This code trains a Faiss IVF-PQ index and adds the same 1 million vectors as compressed codes. IVF-PQ has a different failure mode from HNSW. It can save substantial memory, but it must learn coarse lists and product quantizers before add. IndexFlat L2D is the coarse quantizer, while IndexIVFPQ uses nlist, PQM, and nbits to define the inverted lists and PQ code layout. The coarse lists narrow the search area, and the product quantizer replaces full vectors with short codes. Smaller codes generally help the RAM budget, but they can make distance estimates less faithful. The output shows that training completed and reports the measured combined train and add time. For more practical lessons on AI engineering and retrieval systems, subscribe and keep building with me. Compression helps, but now we need to measure whether wider IVF-PQ searches recover useful neighbors. This snippet measures how Faiss IVF-PQ recall changes when nprobe increases. Query speed alone can hide a weak setting, so recall at 10 compares approximate IDs against truth instead of trusting latency. Recall at 10 means the share of the 10 exact neighbors that also appear in the approximate result. The code searches once with nprobe set to 8, then again with nprobe set to 64, using ParameterSpace. Set index parameter both times. Higher nprobe scans more inverted lists, which often raises recall while doing more work per query. The output shows the recall gain from the wider search and the final recall at 10. We have measured search quality, so the final step turns those measurements into a repeatable deployment decision. This example turns the Faiss benchmark metrics into a small index choice gate. A production RAG index needs more than a fast query path, so the gate checks recall, serialized bytes per vector, build time, and the add-only update pattern. Serialize index gives a compact RAM proxy for both HNSW and IVF-PQ, while HNSW fit and IVF-PQ fit encode the deployment constraints as booleans. The thresholds are intentionally visible so teams can replace them with their own SLA and memory budget. The selector returns the index choice, recall at 10, and bytes per vector. The output shows the selected index and the measured per vector storage that drove the decision. This maps directly to a real retrieval service. HNSW is often a strong fit when you can afford memory and need high recall with simple add-only growth. IVF-PQ is often better when the vector collection is large enough that storing full vectors and graph links becomes costly. In production, keep a held-out query set with known good neighbors. Watch recall after new data arrives, because embedding distributions can shift and reduce the quality of a trained compressed index. The important point is that HNSW and IVF-PQ are not just two speed settings. HNSW spends more memory to navigate a graph of full vectors. IVF-PQ spends more effort on training and tuning so it can store compact codes. Your index should reflect the constraint that actually hurts your system first. Try changing nprobe and compare recall at 10 with the added search work. Then, examine whether the memory savings from IVF-PQ are large enough to justify its lower fidelity distance estimates. What practical vector search topic would you like to explore next? Leave it in the comments and subscribe for more clear AI engineering lessons.